Usually, small signal amplifiers are used for the first several stages of an amplifier system. Therefore, coupling networks are used between the different stages to transmit the modulated signal from one stage to the next without upsetting the bias of the individual stages. One of the most common coupling devices is a simple series capacitor that has a reactance low enough to pass the signal without attenuation while blocking the DC bias levels between the stages. As you can see, the input capacitor C1 passes the signal to the base of the first stage. The signal is then amplified and passed through capacitor C2 into the next stage for further amplification. Since a capacitor will not pass a DC voltage, the bias voltage of one stage will have no effect on the stage it is supplying the signal to. Another common coupling method uses a transformer to electromagnetically couple the stage together. As you can see, the collector resistor of the first stage has been replaced with a transformer. Changes in the collector current are electromagnetically coupled to the secondary of the transformer. The transformer secondary is then connected to the input of the next amplifier stage. Again, the DC bias voltage of the first stage is isolated from the base voltage of the second stage. Both the transformer and capacitor coupling methods are used for amplifying AC signal voltages. When using the voltage divider bias circuit, the current will flow through both the emitter resistor RE and the load resistor RL. Even though the primary purpose of the emitter resistor is in its stabilizing effect in the bias circuit, it will develop some of the signal voltage across it, which in turn reduces the output voltage drop at the collector. This results in a decrease in the gain of the stages. Therefore, in small signal amplifiers, the emitter resistor RE will be bypassed with a large capacitor CE. Capacitor CE will provide a low impedance path for any AC signal current. This eliminates any reduction in gain caused by the emitter resistor. The ideal small signal amplifier should amplify all frequencies equally within the linear portion of the characteristic curve. But due to the biasing circuitry and coupling circuitry of the amplifier, this ideal situation cannot exist. As you recall, the reactance of a capacitor depends upon the frequency being applied to it. The reactance increases as the frequency decreases. Therefore, at low frequencies, the coupling capacitor may attenuate the incoming signal. If the reactance of the capacitor exceeds about 1/10 of the circuit's input resistance, the gain of the circuit will be reduced. The emitter bypass capacitor and the output coupling capacitor will also affect the gain of the circuit at low frequencies. This will result in a reduction of the output signal. At higher frequencies, the intercapacitance of the transistor will reduce the gain of the amplifier, again resulting in a reduction of the output signal. Here we see the frequency response curve of a typical amplifier. As you notice, the voltage gain is fairly constant for the middle portion of the response curve, and the gain drops off appreciably at each end of the frequency response curve. When the gain falls to 0.707 of the response curve, the signal is said to be at the cutoff frequency point. There will be a cutoff point at the low frequency end and one at the high frequency end. The range of frequencies between these two cutoff points is called the passband frequency. At the cutoff points, only 1/2 of the power is available. Therefore, sometimes you will hear the cutoff points being referred to as the half power points. The perfect amplifier should have an infinite input impedance with a zero output impedance. This would allow the stage to operate so there is no current drain from the previous stage, and at the same time have an unlimited ability to drive the next stage. Unfortunately, most small signal amplifiers will use the common emitter configuration, and it rates poorly in both of these parameters. The typical input impedance of the common emitter configuration will usually be around 3,000 to 4,000 ohms, while the output impedance will be fairly high, usually around 50,000 ohms. After the weak signal has been amplified sufficiently, it is fed into a power amplifier to develop the power necessary to drive the output load. Audio power amplifiers are biased Class B. As you recall, the Class B amplifier is biased at the cutoff point. Therefore, current will only flow through the Class B amplifier when it is driven into conduction by the incoming signal. Since current only flows in the Class B amplifier for half of every cycle, it generally requires the use of 2 transistors to amplify the incoming signal. Each transistor will amplify half of every cycle. We call this arrangement a push-pull amplifier. As you can see, when the current through one transistor increases, the current through the other transistor will decrease. The increasing magnetic field produced in one half of the output transformer is aided by the decreasing magnetic field produced in the other half of the transformer. This gives the effect of one transistor pushing while the other transistor is pulling. From this illustration, we see when the top of the secondary on T1 is positive with respect to the bottom of T1, the signal current will flow from the center tap winding into the junction of R3 and R4. At this point, Q1 is forward biased and Q2 is reverse biased. Therefore, the current will flow through R1 and into the emitter base junction of Q1. A small percentage of the current flowing into Q1 will flow through the base area and back to the top of the secondary of T1. The remainder of the current will flow through the collector of Q1 and into the top of the primary of T2. From here, the current will flow from the center tap back to B+. A small bias current will flow from the common through R4, then through R3, and into the positive side of the power supply. When the input signal reverses and the top of the secondary of T1 becomes negative with respect to the bottom of T1, the current will flow from the center tap on the secondary of T1 into the junction of R3 and R4. At this point, Q1 is now reverse biased and Q2 is forward biased. So the current now flows through R2 and into the emitter base junction of Q2. Some of the current will flow through the base and back to the bottom of the secondary of T1. The remaining current will flow through the collector of Q2 and into the bottom of the primary of transformer T2. From here, the current will flow to B+. Once again, a small bias current will flow from the common through R4, then through R3, and back to B+. As you saw earlier, distortion cannot be avoided in a Class B amplifier. Therefore, it is common practice to drive the amplifiers as hard as possible to obtain the maximum efficiency. Class B amplifiers are used where high efficiency and high output power is required and where a small amount of distortion can be tolerated. The typical efficiency of the Class B amplifier will be around 50 to 60%. So far, we have examined the Class A amplifier and the Class B amplifier. We have seen that the Class A amplifier was biased at the midpoint of the characteristic curve and that it operated with very little distortion. Since the Class A amplifier draws current even when no input signal is applied, it is a very inefficient circuit. The Class B amplifier, on the other hand, was biased at the cutoff point. Therefore, the Class B amplifier will have a small amount of distortion and is more efficient since it only draws current when it has an incoming signal. The Class B amplifier is also generally operated in a push-pull operation, which requires the use of 2 transistors and a center tap transformer. The push-pull amplifier can also be biased as AB1 or AB2 amplifiers. This places the bias point between the Class A and Class B operating points. To obtain even higher efficiency, it is necessary to bias the transistor far beyond the cutoff point. Such an amplifier is called a Class C amplifier. By increasing the reverse bias of the transistor, it also increases the distortion of the output signal. The resulting output waveform will not even be half of the input waveform, but instead will be a series of pulses formed by the very top of the waveform. The current will flow through the transistor for a small percentage of the input cycle. Since the Class C amplifier cannot be used to reproduce the incoming signal because the distortion is too great, it is generally fed into a tank circuit, which is tuned to the input frequency. The flywheel effect of the tank circuit will restore the signal to a sine wave, which will operate at the resonant frequency of the tank circuit. Since the tank circuit is tuned to a certain band of frequencies, It will respond to a relatively narrow band of frequencies. The Class C amplifier is generally used to amplify the output of an oscillator circuit. The efficiency of the Class C amplifier will typically be 70 to 80%. We will now pause for a short review of the most recent material discussed. Class A amplifiers are generally used for the first few stages in many amplifying systems. This is due to the fact that Class A amplifiers will reproduce the incoming signal with very little distortion. Class A amplifiers are biased at the midpoint on the characteristic curve, so the amplifier can amplify the incoming signal by equal amounts along the linear portion of the curve. Capacitors and inductively coupled coils are used as coupling devices between amplifier stages so that the biasing arrangement of one circuit does not affect the circuit it is feeding. Class B amplifiers are generally used as the final stage in the amplifier system. Class B amplifiers are designed for power and will typically use 2 transistors in a push-pull configuration. Since the Class B amplifier is biased at the cutoff point on the characteristic curve, it will produce some distortion at the low frequency end. Class B amplifiers are used when high efficiency and high output power are required. It is common practice to drive the Class B amplifier as hard as possible to obtain maximum efficiency. Since the Class B amplifier only draws current when there is an incoming signal, it has a typical efficiency of approximately 60%. To obtain an even higher efficiency amplifier stage, it is necessary to bias the transistor far beyond the cutoff point. Such an amplifier is called a Class C amplifier. Increasing the bias point beyond the cutoff does create significant problems for audio or video reproduction. The signal will no longer be a faithful reproduction of the input, but rather it will merely be a series of pulses. Since the Class C amplifier cannot be used to reproduce audio or video information, it will generally feed a tank circuit, which is used to restore pulses back into a sine wave, the frequency of which will be that of an incoming signal. Class C amplifiers are generally used to amplify the weak signals produced by an oscillator circuit. The efficiency of the Class C amplifier will typically be about 80%.